Today, we are jumping headfirst into a massive cosmic detective story. It turns out the single biggest ingredient in our universe, this thing we call dark energy, might be acting, well, a little weird. And brand new clues are suggesting it might be changing its very nature as we speak.
So let's get right to it. This question really gets to the heart of a giant puzzle in cosmology. You see, dark energy makes up most of, well, everything. And for decades, we've had a pretty simple, straightforward idea about what it is. But what if that idea is just wrong? What if the most dominant force in the entire cosmos isn't some constant, unchanging thing at all?
Well, that's the incredible possibility of this being raised by some brand new results from the Dark Energy Spectroscopic Instrument. We just call it DESI. These new measurements are giving us the strongest hints we've ever had that our standard model of the universe might need a serious rewrite.
Okay, so what exactly is this stuff? To put it simply, dark energy is this invisible force that's pushing everything in the universe apart from everything else. It's actually making the expansion of the universe speed up. It is, without a doubt, the biggest player in the whole cosmic game. But here's the crazy part. We know almost nothing about it.
For a really long time, our best theory, that's called lambda CDM, has basically treated dark energy as a cosmological constant. Just think of it like a smooth, unchanging energy that's just woven into the very fabric of space-time itself. It's simple, it's elegant, and, it might not be the whole story.
And this is where the plot really thickens. This new data from DESI gives us this really tantalizing clue that dark energy isn't constant. Instead, it looks like it might be dynamical. And that just means its strength, its behavior, could actually be evolving as the universe gets older. I mean, this is a potential revolution in how we see everything. But of course, this brings up a huge problem. I mean, if you can't see dark energy, you can't touch it, how on earth do you go about measuring its behavior? And this leads us to what I'm calling the proxy problem. So scientists use this thing called the equation of state, which they represent with the letter W. The whole idea is actually pretty simple. If W is exactly -1, then dark energy is that cosmological constant we talked about, unchanging. But if W is any other number, or if it changes over time, then boom, dark energy is dynamic.
And this is the absolute key right here in this quote from the source paper. You can't just, stick a thermometer into the universe and measure W. It doesn't work like that. Instead, scientists have to measure things they can see, like how far away galaxies and supernovae are, and then they have to work backwards to figure out what W must be.
And to do that, they use these different mathematical formulas called parameterizations. The best way to think about them is like different lenses you can put on a camera. Each lens makes slightly different assumptions about how W might be changing, and it helps turn all that raw data into a coherent story about dark energy.
But right away, this leads to a super important question. If you get a surprising result, is it a real discovery, or is it maybe just a flaw in the specific lens you were using? To really trust the clue, you absolutely have to test your tools first.
So, the researchers behind this paper decided to focus on the 4 most common tools, or lenses, that cosmologists use. You can think of them as 4 different detectives, right? Each one has a slightly different method for investigating the case. We've got CPL, JBP, BAE, and EXP.
And that really brings us to the central question of this whole thing. If you give all 4 of these detectives the exact same set of clues from the DESI survey, do they all point their fingers at the same culprit? Or do they start arguing with each other? This is what we need to find out.
So, after putting all of these different tools to the test, what did our detectives find? Well, the first big verdict is in, and let me tell you, it is a big one. The evidence is solid.
So here's the headline. The conclusion is robust. It actually doesn't matter which lens you use to look at the data. CPL, JBP, BA, EXP, all 4 of them totally independently point to the exact same conclusion. The data we have strongly favors a dark energy that is changing over time. The clue holds up. But wait, the story does not end there. Because by confirming that their tools were reliable, the scientists realized they could do something even more exciting. They could start using those tools to identify actual suspects, to test specific physical theories about what dark energy could really be.
They zeroed in on 2 main suspects. Over on the left, we have minimal quintessence. Think of this as a new energy field that's driving cosmic expansion, but otherwise it just kind of keeps to itself. On the right, we have non-minimal quintessence, which is a much more complex idea where this new field doesn't just push things apart, it can actually interact with and change the force of gravity itself.
So now the whole investigation has shifted gears. We've moved from just confirming a clue to actually building a case against a specific suspect. It is time to see which one of these theories actually fits the evidence that DESI has given us.
Now, to really get what comes next, let's use a little analogy. Imagine that all of this new DESI data draws a target on a wall, okay? So any theory that wants to be taken seriously has to be able to hit that target with its predictions.
So what happened when they put the first suspect to the test? Well, minimal quintessence, that simpler theory, it almost completely misses the target. It's not even close. Its predictions fall way outside the zone that the data says is correct. So yeah, that makes it a really poor fit for what we're actually seeing out there.
But then they tested the second, more complex theory. And wow, this is a direct hit. Non-minimal quintessence lands its predictions squarely inside the data's target zone. There is this incredibly compelling, significant overlap between what the theory says should happen and what the DESI survey is actually seeing.
And look, this isn't just a pretty picture. The numbers absolutely back it up. This table shows how much better each model fits the real data compared to that old cosmological constant idea. All you need to know is that a bigger negative number is better. And just look at that bottom row. Non-minimal quintessence is an excellent fit, even better than the best-fitting mathematical model they tested.
So, why does any of this matter? It matters because this whole rigorous process has completely shifted the conversation. We're not just asking if dark energy is changing anymore. We've moved past that. We're now asking a much deeper question. What is this changing dark energy? For the first time, we have a viable, testable new theory on the table.
And it really all comes back to this one powerful line from the paper itself. The conclusions are solid. They're not some fluke that depends on one particular way of looking at the problem. The evidence for this whole new picture of our universe is robust.
And so, that's where we are. For the first time, we have a specific, compelling theory for the biggest mystery in all of cosmology that just fits our best evidence better than anything else we've got. We've just been handed a major clue in the case of the shifting universe. The only question now is, where does it lead us next?